Hi students, hope you are doing fine. Today we are going to start optimization tutorial 20 and today we are going to discuss the Newton's method in optimization. I am Dr. Ganguly. Now in today's tutorial you are going to learn about the classical Newton method which was propounded in 1669, the modified Newton method. Then we are going to talk about some safeguard techniques which are required in case the Hessian matrix becomes non-positive definite. Now if we look at the classical Newton method, it has the form given here in the equation in green, that is xk plus 1 is xk plus dk. Dk is the search direction, xk is the current point, xk plus 1 is the next point. Now the modified Newton method simply uses the one-dimensional step size, that is alpha k here. So in that case the equation in blue becomes xk plus 1 is xk plus alpha k dk, and to obtain alpha k we have to call some algorithm which deals with one-dimensional search. We are going to use Python code to actually look at these concepts today. Again, if you are not familiar with the theory, take a look at optimization lecture 20, Newton method. In all these tutorials, we are essentially creating a tutorial in response to the lecture because some of the students have suggested that they do not understand too many things from the math. They would like to see some examples and the code. So let's look at the Newton's classical method closely. So essentially you have to start with the point x0. This point needs to be given, and then you calculate the search direction using this equation here, that is hk dk equals minus ck. Now here of course ck is the gradient vector, hk is the Hessian matrix, all these at point k. So you essentially have access to xk, and then you can calculate ck and hk at that point xk. Now using this system of equations you can obtain dk. So remember dk is a vector, ck is a vector, and hk is a matrix. So these are all of dimension n, where n is the number of design variables for the problem or the length of the design vector x. So then we move in the design space using this formula here, xk plus 1 equals xk plus dk. Now one of the things to remember is that in the Newton's method, the Hessian matrix should remain positive definite, and also it should not be singular, because if it's singular then you cannot solve this linear system here, h d is minus c. So the solution of this system requires that h should not be singular, and we will also see that h should not be positive definite, or should be positive definite, because that's going to help you to satisfy the descent condition for this particular method. Now one of the interesting things is that if you can show that h is positive definite, then it's also going to be a non-singular matrix. So that comes out of that particular logic, because remember here what's going to happen, the determinant is going to be greater than 0, and so it's not going to be equal to 0. Now as far as the Newton's method in practice, or the modified Newton's method, is there, all you do is that you add this alpha k term here when you move around in the design space. So the remaining things are exactly same as in the classical Newton method, that is x0 is given. You find the search direction by solving this linear system, hd is minus c, and then you move around in the design space using this formula, xk plus 1 is xk plus alpha k dk, and you obtain alpha k using a one-dimensional search. Again, remember to check that the Hessian matrix should be positive definite and the Hessian should not be singular. Now let's put all these theories into practice. We want to write a Python program for the classical Newton method, and again we are going to use our usual formula here, or rather function, that is fx is x1 square plus 2x2 square plus e to the power minus x1 minus x2, and we are going to start from the point x0 is 5 minus 5. So before we move forward, let us just remember the minimum point. So the minimum point was x1 is 0.31277 and x2 is 0.15638. These are essentially obtained from the Lambert W function. If you are interested in more details, look at optimization tutorial 3. where I have obtained these by setting the gradient vector to 0 using the optimality criteria. Now the Lambert W function has this form here that when this function works on some expression a e to the power a, it essentially gives you a. So that's the definition of the Lambert W function. It's a special function very similar to the other special functions out there. For example, Bessel function, gamma function, and so on. Now let's start building up the functions required for the Python code. So let's look at the math function here, x1 square plus 2x2 square plus e to the power minus x1 minus x2. So we have this function here, f of x, which essentially returns this math function. And what I do here is I calculate this expression exponential e to the power minus x1 minus x2, and then I put this in this term here. Now, of course, you need to call numpy in the main program to use the exponential function. Now let's look at the gradient vector. So this is a vector given here. It's obtained by taking partial derivatives of f with respect to x1 and x2. And then I put it in this function here. So you can see it returns to me this term 2x1 minus e to the power minus x1 minus x2 and 4x2 minus e to the power minus x1 minus x2. These are coded in here. Again, the term here refers to e to the power minus x1 minus x2. Now the Newton method requires something more, and that is the Hessian matrix. So we can calculate this matrix by taking the gradient and then again taking the second derivatives of this gradient. So what's going to happen is that this is the second derivative with respect to x1, this is the second derivative with respect to x2, and these two are the cross derivatives. So this is going to be d2f by dx1 dx2, and this is d2f by dx2 dx1, and these are going to be same. So the Hessian matrix is symmetric. Now once we have this matrix here, we can code it in as follows. So here what's going to happen is that we have this function h, and this function returns to me the h matrix. Now one of the things we always do in programming is that if we have something being repeated several times, for example the term e to the power minus x1 minus x2, we can simply define it once and we can use it several times in this program. So you here can see that it is 2 plus term, this is term, this is again term, this is 4 plus term. So I have used this common definition of e to the power minus x1 minus x2 only once and then put it in the Hessian matrix, and I am returning this matrix back. Now, like I mentioned before, we need to check for positive definiteness of the Hessian matrix. So in general, if there is a matrix A, we can check its positive definiteness by checking out all the eigenvalues for that matrix. So essentially that's what's going to happen here. If all those lambdas are greater than 0, then I'm going to return true, else I'm going to return false. So this is a very simple function which accomplishes this particular aspect. Now, why should this H matrix be positive definite? Now you can see from the line search criteria given here, that is CKT dk less than 0, or rather I should say the descent condition, that if I take this particular search direction and I combine it with the descent condition, then I'm going to get this expression here, which is nothing but the mathematical form of telling me that H is a positive definite matrix. So this corresponds to a positive definite quadratic form. So if this holds, then the descent condition is going to be satisfied. Remember, the descent condition is CKT dk is less than 0. Let's now start looking at the main program. So this is the very simple main program here. We import numpy, we put in the starting point here, which is 5 minus 5, and we use a small number tolerance and we use max is 1000. The tolerance is essentially going to be used to check the convergence of the method. The max is something which we will use to build up the for loops. We print Newton method results, and then I call the Newton function here, which takes in the starting value x0, the tolerance small number, and the max value of 1000. Let's now build up this classical Newton function. So remember, classical Newton function is going to be very easy because there is no one-dimensional search here. So what we do is that we start off with x is x0, that is the starting guess. Then I have the for loop here. I put the gradient vector in C, And I have this situation that I check for the H matrix being positive definite. So H at X, it should be positive definite. If it's true, I print that H is positive definite. I print the current value of I and I print X here. Now what I do is I use this particular solver which is built into NumPy to essentially solve the system HD is minus C. So it's going to take H and C and it's going to return to me D. So I have to put H here, I have to put minus C here, and I get the solution out here. Then I simply write X is X plus D, which is this expression xk plus 1 is xk plus dk. Now in case the H matrix is not positive definite, then I simply print that H is not positive definite and I break out of the for loop. And finally I have this statement that if the norm of the gradient vector is less than the small number tolerance, remember I put tolerance to 0.00001, then I print converged X, I print X and I break out of this loop here. So when I run this code, I get these results here. So of course, as far as the particular matrix we have looked at is concerned, it is always going to be positive definite. And so I get that here. I get the values of I. I see X starting from 5 minus 5 and extremely rapidly converging to the optimal solution, that is 3.27 7 and 0.15638. So Newton's method is very speedy in terms of convergence. That's something which is very important to remember. It has quadratic convergence, and especially you can see in a problem here which is kind of like a quadratic type of function, its convergence is extremely rapid. Let's now look at the modified Newton method where we are going to use the one-dimensional step size. All the remaining things remain same. So all I need to do is look at the main program and the Newton function and modify it so that I use the one-dimensional search. So again, the main program remains exactly as before. So I import NumPy, I give the starting point 5 minus 5. I have the tolerance as a small number, max at 1000. And I essentially invoke the Newton function with x0, tall and max, and I print Newton method results. Now here there is a slight modification in the Newton function. So this is the modified Newton function. So the key modification is that I now have alpha and I call this particular function here equal to get this value of alpha. So what's happening is that equal takes in tolerance, the small number dx at the current point, max, which is the large number for the for loop, and then it returns to me an estimate of the appropriate value of alpha given the corresponding d and x. And then I check out whether the Hessian is positive definite. I print I print alpha, I print x, and I update x as x plus alpha d. So the difference here is that this alpha k is now coming into this problem here. Remaining parts are all remaining the same. So I'm going to need one more simple function for the one-dimensional search, and that function is f1d. So this function is going to take in alpha, d and x, and it's going to return the function value of x plus alpha d. So remember, this is the next point in the design space. So what this function does is that it's going to take in various different values of alpha and it's going to return the function. So that's going to help the 1D search function essentially calculate these particular values and find the optimal alpha. Let's look at the 1D search. So again, the 1D search I am going to use is a very simple one. So I start with alpha as some delta, 2 delta, 3 delta, all the way like this. And I bracket the minimum to these 3 points, q minus 1 delta, q delta, and q plus 1 delta. So you can see these 3 points here, and q is going in a loop here to max. And then what I do is I check this particular value. So this is required to essentially bracket this minimum point. So what happens is that the function value keeps decreasing and then after a point it starts increasing. So that's the bracket here which we have obtained. When this condition in the if statement is satisfied, at this point I can essentially declare a star as the optimal value for alpha, the estimate of the optimal value. I declare I as AU minus AL or alpha U minus alpha L. So in the program I am using A in place of the Greek letter alpha, and then finally you are seeing what happens is that I divide delta by 10. So each time I'm going to divide it by 10, and then I'm going to set A is AL again. Remember I'm starting at A is 0, And so then this interval has been bracketed, and then I divide this into many small parts, and I continue this process till I converge, and finally when I have converged, I return A star here. So A star is being calculated here inside the for loop. Now if you want to revise this method or look at it, take a look at optimization tutorial 7 on this particular one-dimensional search. Let's look at the modified Newton results. Very interesting results in that you start from the same point 5 minus 5, you converge extremely rapidly, and the alpha value is almost near 1 in this particular problem, because again this is a quadratic type of function, so it actually is almost close to the classical Newton method. But this is not always going to be the case. We will look at a more nonlinear function next, and we will explore the possibility of the Hessian matrix not being positive definite. So let's look at that. So that brings us to question 3, and this is to write a Python program for the modified Newton method, which we did previously. And now we are going to use the Rosenbrock function, and we are going to use two starting guesses here. So one is going to be 0, 0, and the second is going to be 0, 0.005. So the first guess is going to be something in which the Hessian remains positive definite at all points. But the second one I have structured such that there is a situation where the Hessian is not positive definite and it may not lead to a singular non-singular matrix. So let's try to do this problem. Again, remember, for this Rosenbrock function, x star is 1, 1. If you are interested, you can calculate it. I think I have done it in some previous tutorial, maybe in the optimality criteria and so on. So let's start with this function. Of course, I have changed the math function, so I have to change the fx function here in Python. So I have changed it here also. So it is 100 x2 minus x1 square plus 1 minus x1 square. So of course in Python you have to change the notation here. So remember, x1 is going to be x0 and x2 is going to be x1. I need to then put in the gradient vector. So this is the gradient vector for this function, the partial derivatives of this function with respect to x1 and with respect to x2, and I have coded it here. So now, like I mentioned before, whenever you see some term is being repeated, for example x2 minus x1 square, you can put it as some expression here, like I put this term and then put it in the actual code here. So that kind of simplifies the code to some extent and prevents recalculation of some of these functions. Now the Newton method will also of course require the Hessian matrix. So this is the Hessian matrix for this function. Again, we have coded it here, and so this is going to give me the Hessian matrix at any point x. So when I give in a vector x here, I'm going to get h of x out of this. Let's first run it from the nice point, that is 0, 0, and again I have basically put this point 0, 0 here, and I call the Newton function. So you can see here now the convergence is somewhat slower because this is a slightly more complex problem, slightly more nonlinear, and you can see here that various values of alpha, or the one-dimensional search, are being used, the results of the one-dimensional search, and these are not necessarily always very close to 1. But you do see that you start from 0, 0 and we do converge to 1 and 1, which is the optimal point. And of course, throughout this particular problem, the Hessian is positive definite at each step. Now, what we are going to do is we are going to use this starting point, and this is going to actually trigger this else part of the Newton function here, that the Hessian is not positive definite. And how I came up with this point is that I actually took this part of the H matrix and I set it equal to 0, and I basically put x1 to 0, and that led me to x2 being 0.005. So that's going to cause the first point itself to become singular and also the Hessian matrix to not be positive definite. So that's what happens when I use this particular point and run the code, the same main program, the same Newton and so on. I essentially get the output as Newton method results Hessian is not PD. Now that's not a good solution in all cases. Of course it's a check, but we can build in a certain safeguard into the problem here. So that's what I've done here. So if the matrix H is positive definite, I essentially follow the Newton method. That is, I use the equation HD is minus C to solve for the d here, and then I continue with that. But in case h is not positive definite, I actually set h to I. So this is a very simple and kind of nice solution to this problem, because what it will do is that now I have to solve this system here. I'm using the same type of solver. So here what you can see if you look carefully at this method is that this is the steepest descent method or the gradient descent method. So this is dk is minus ck. So in fact we can think of the steepest descent method as a special case of the Newton method when h equals I. And so here I have coded in the I matrix here. Remember I is going to be 1 0 0 1, and then I use the same solver to solve for I mat and minus c. So I have replaced h of x by I mat, which is the identity matrix here. So what this is doing is that it's doing Newton method as far as the Hessian matrix is positive definite, and when it is not, it is replacing the H matrix with I. Remember I is of course positive definite, and then it is using this method here. So we can say that it is actually going back to steepest descent for this particular step. And each case we are calculating the one-dimensional search or using the one-dimensional search to get the optimal value of alpha, and then we are using x is x plus alpha d, and we are converging when the gradient vector becomes very small. So let us look at the results with the safe Newton method. So again this is the starting point which causes the singularity, and then I again invoke the call to this Newton method which I have slightly changed to make it safer. And now you can see this method runs without any problem. The first case happens when x0 is 0.005. In that case, Hessian is not positive definite. So we set h to 1 or identity, and then we solve it. So this first time around it is actually using the steepest descent search direction. It is setting h equals I. And then beyond it we can see that h is positive definite, and so again we converge very beautifully to 1 and 1. Now this is something which is very interesting, and this simple approach can be used in the Newton method as well as in the quasi-Newton methods which we are going to discuss later. Now there are more sophisticated ways of handling this problem, because very often we use something known as the LDL decomposition and all in solving linear systems, and you could actually try to look at the D matrix there and make the negative part or the zero part positive there, or replace that by 1. But again a simple way is the one which I have suggested here also. This is something you can use as a safeguard technique in your Newton code. Let me give you a homework problem so you can keep yourself busy. So let us try to create an algorithm which starts with steepest descent and then keeps changing between steepest descent and Newton as you go from k is 0 onwards. So when k is 0 we use steepest descent, k is 1 Newton method, k is 2 steepest descent, k is 3 Newton method, k is 4 steepest descent, k is 5 Newton method, and so on. You get the point. And try to use this particular code to check out the results and see how they compare with pure Newton and pure steepest descent method. So this will give you some exercise or some entertainment in terms of solving this particular problem. So today's lecture we learned about a very important, very classical method, the Newton's method. It is kind of astonishing that Newton made so many contributions around so many different fields, not only in physics, in mathematics, in calculus, but also in some important areas of optimization. For example, the problem we have looked at today. And Newton's method are very important because they provide the thinking behind the quasi-Newton method, which we are going to discuss later. In the quasi-Newton method, you don't use the H matrix, you build up the H matrix by using the gradient vectors from the previous points and the search directions from the previous point. So this Newton method is something which is very important, but of course you can realize it is not going to be used for many problems because the calculation of the Hessian matrix is often very difficult. But if you do have functions for which you can calculate the H matrix, nowadays remember there are a lot of symbolic softwares out there such as Mathematica. For example, Wolfram itself is there on the internet. Then you can very simply calculate the second derivatives of a given function, and you could actually calculate the H matrix without much problem. But in many realistic problems, particularly in engineering optimization, you do not have the Hessian matrix. The Hessian matrix has to be calculated numerically, and in that case the finite difference calculation or the central difference calculation using numerical derivatives is going to become very much computationally expensive. So again, let us review some of the things we studied today. We looked at the Newton method. We looked at the classical Newton method, which had a step size of 1. We also saw that we can bring in a step size from 1D search, and then that leads us to the modified Newton method. And we also saw in case the H matrix became non-positive definite, you have certain problems in terms of the descent condition not being satisfied. But this particular problem can be mitigated by some simple techniques. For example, we can simply set H to I. Now this also leads us to the interesting thinking that maybe H is not so sacrosanct, and maybe if we simply have an H which is positive definite and non-singular, we can probably do a good job with this particular type of problem, because for example we have seen that the steepest descent method itself is nothing but a Newton method which with H equal to I. So since that works very well, we now can have some idea that maybe we can have an H better than I, but not necessarily the actual H. Now that's some of the thinking behind some of the methods we are going to study next. So we are going to study the Marquardt method, which is based on the thinking I showed to you today, a combination of steepest descent and Newton, and then we are going to start looking at the quasi-Newton methods and so on. Again, make it a point to review optimization lecture 20 on Newton's method to learn the theory behind some of the things which we discussed in the tutorial today. And if you go back between the lecture and the tutorial, you are going to get maximum value out of these videos and this optimization course.